up to now, up until this last class, we've been dealing with, where numerical variable is concerned, we've been dealing with statistics that are related to a normal distribution. The idea of a mean, okay, if it's a population mean, we call it mu. I'm going to call this one 100. If it's a population standard deviation, in other words, spread, we call it standard deviation, but we use a sigma, the Greek letter sigma, to represent it if it's a population. Okay, and we know there are certain properties here to this normal distribution, to any normal distribution, and that is that, for instance, that within 2 standard deviations to the left of the mean and 2 standard deviations to the right of the mean, we have 95% of the probability of picking a random person or item from this distribution within that range, or 95% of the people if they're patients or so on and so forth, or subjects. So we have 95% between 2 standard deviations above and 2 below. We call that the empirical rule. It's a general rule. It's an estimate, but then we know we have another table called a z-table where we have the actual probabilities for this occurring. This is based on a formula. This is a formula based on probability, based on how chance in selection is going to affect a normal distribution. Okay, this z-table now, actually, when we look at the z-table, if we look up specific values, number of standard deviations, which is really what z stands for. Z really stands for the number of standard deviations away from the mean, right? So if we look up, for instance, what percentage is represented by -2 to +2 standard deviations from the mean, it's really actually a little bit more than 95%. It's more like 95.5, not 95 point, I'm going to say 6% for argument's sake, a little bit more, right? So on the other hand, we know it more accurately. It's a little bit more tedious to look it up. We know it more accurately, but what that means now is that we're not stuck with only looking at whole numbers as the number of standard deviations away from the means in order to know something about this distribution. Now we can find any values z-score. So you could have a z-score, for instance, if we were looking at what percentage of this population was below 86.5, for instance, you could determine a z-score for that 86.5. Okay, z is equal to x minus mu, the difference between the value, in this case 86.5, and the mean, over the standard deviation. So that would be 86.5 minus 100 over 10, and that would be equal to 13.5 or 1.35, right? Did I get that right? Yep. Okay, that would be that's the number of standard deviations, positive or negative.
Which one? Negative.
Right, exactly. It's negative from the math, right? Even beyond the math, you know it's negative because it's to the left of the mean in this case. So which we can determine the area that is represented to the left of that value 86.5 by looking it up on our z-table. We could also use Excel, right? There's a function norm sdist in Excel where we just put in the z-score, just 1.35, and it gives you this area, right? Same as the table would. Or we could use norm dist, and then in that it would ask you for the value x that we were looking at. It asks you for the mean, it asks you for the standard deviation, and it asks you to fill in true or false for cumulative. In the case of this function, you're always going to fill in true, right? Because you're always looking for an area, the whole area, not just some value, some skinny little value for that one number, right? So that would actually give you the same value. P, we sometimes call that P, the probability of picking an individual or a subject that's in that portion of this distribution, right? So now that we know that, we want to move on to something that we can know practically, because it's nice to know this, but the problem is in reality, we never know what the mean is, and we never know what the standard deviation is for the population, because the only way to know that is to measure everybody in the population. So we're stuck with knowing what we know about this population by sampling. Okay, so let's see what happens when we sample. Well, it turns out that if we take this same population, right, mean is 100 and standard deviation is 10, and we're making believe we actually know that about this population. Turns out that if we take a sample from this population of a certain size, I'm going to say n equals n equals 25, sample size of 25. If we sample 25 people in this population, we're going to wind up with a number for what that value is. If we get really lucky, we're going to call that x bar because it's not the population mean, it's a sample mean. If we're incredibly lucky, we'll get 100. We'll get the same number as the population mean. But we're never that lucky, right? I don't know about you guys. Anybody with a car at Atlantic City recently? No, you haven't, right? So we're not that lucky, right? So what's going to happen is sometimes we're going to get a number less than that. Sometimes we're going to get a number higher than that. So again, if I do it again, if I keep doing it over and over again, right, I'm going to get different values each time I take that sample. If I take all of these x bars of sample size 25 and I plot a new distribution, this is what it's going to look like. It's going to have roughly the same mean as the population distribution, but it's going to have a smaller standard deviation. I'm not going to use the sigma. I'm going to use SD instead because we're dealing with a sample. I'm going to use X bar down here. It's not going to be as wide, right? There's a relationship between the sample size and how spread out this distribution is. If we had a sample size n equals 100, then the values would all be closer to 100 than if we have a small sample size. Small sample size, we're going to get a lot of variability. Sometimes we'll underestimate it or overestimate it much more than we would if we had a sample size of 100. So a sample size of 100 is going to be even narrower than our sample size of 25. But it's still, center is going to be X bar because these are all going to, half the time you're going to have a sample below the mean, half the time above the mean, right? So now, what's the relationship between this? As it turns out, the relationship between the standard deviation for the population and the standard deviation for the sample means is equal to the standard deviation of the population, sigma, divided by the square root of the sample size. Makes sense. As the sample size gets bigger, we're dividing a bigger number into the standard deviation of the population. The standard deviation of the sample gets smaller, right? Gets narrower, right? So for instance, in the case of 25, the standard deviation for this distribution of sample means is going to be 5, it's going to be 10 divided by 5 or 2, good. And for this one, it's going to be 10 divided by square root of 100, 10 by 10, that's going to be equal to standard deviation, is going to be equal to 1, right? So it's narrower. Okay, so now, that's interesting, right? But so far not useful. Interesting so far, but not useful. It's going to become very useful very quickly. Okay, so now, here's our standard deviation. Here's our we keep using the term standard deviation, right? Yes, this is standard deviation of population. I use a different letter, but I still call it standard deviation. I want to be careful not to mix these up. In order to not mix them up, when I take repeated samples of a certain size and I plot a new distribution, instead of calling that the standard deviation, I'm going to give it a new name. I'm going to call it the standard error. Right, same thing. It's the standard deviation of the samples, but I'm going to call it standard error. So from now on, if I say the standard error is equal to 2, you know I'm referring to a sample distribution, not the population distribution. Right, easy way to distinguish between the two of them. So now how do I apply that? Okay, so now this is where things get really interesting. Okay, so oops, really, really interesting. Okay, so let's say I take a sample. I'm going to say for the moment, I don't know what mu is. Don't have any idea. For the moment, I'm going to say I know sigma is 10. Yeah. I'm just making that up because because I'm going to calculate the standard error. I want to know what the standard error is going to be, right? And to tell you the truth, it makes it easier if I know that sigma is equal to 10. So for the moment, you're going to have to trust me on this. When we're really doing this, we're not going to need to, when we're really using this practically, we're not going to need to know the standard deviation of the population. For the moment, it helps us to know it because it eliminates one area of uncertainty that we don't need. We're focusing more on the mean right now, right? So I'm gonna make believe we know it, even though we don't know the population mean. Sometimes, in effect, in real studies we say that we do know it. Could you imagine we do a study where we previously had sampled a very large population of, say, children in the Bronx, and we measured their blood lead levels, and we sampled every child in the Bronx. Turned out the standard deviation was 3 micrograms per deciliter, 3 standard deviation for the whole population of kids in the Bronx. And they do this, right? There's a certain age where all children get tested for lead when they start school. So we know it's 3, right? So now let's say we're going to go back 10 years later, like to Flint, Michigan, and now we're concerned, but we don't have the resources to test everybody. So we're going to test 100 kids or 500 kids, right? So we might say to ourselves, okay, I'm going to test these 100 kids. And I'm going to find out what X bar is for those 100 kids. But you want to know something? It may be probably more reliable to use the standard deviation for the whole population that we had determined 10 years ago, because it may be that we could argue that the mean, the level of blood on average, lead in the blood for those children may have changed, but on average, but we don't have a lot of reason to believe the variability changed in those numbers, right? So we might be able to justify saying we know the standard deviation, or we know it better than estimating it from the sample might be, right? There might be reasons why we might do this. So it's not entirely a possible situation. But we're doing it not so much because there's a clinical reason or a mathematical reason for us to do it. We're doing it because it's convenient for right now. Okay, so let's say that I take a sample from this population. I don't know what I mean. I take a sample of size 36, right? So now I say to myself, okay, I don't like 36. Let me pick another number. Let's make the standard deviation of population 12. I'm thinking a little bit ahead here because I'll make things easy. Standard deviation is 12, sample size is 36. Okay, so now I take a sample size 36, and it turns out that the mean X bar for those 36 people is equal to 50. I don't know what the population mean is. I'm never going to know what the population mean is. I know I took a sample. 36 is a decent sized sample. It looks like the mean is probably around 50. Could be 49, could be 47, could be 52, right? But it looks like it's around 50. But, I can't really depend on that, can I? Well, let me see what would have happened if I would have known that it was 50 and the standard deviation was 12. What would repeated samples of size 36 look like? Okay, well, repeated samples of size 36 would look like this. This would be 50, and 36 divided by, 12 divided by, divided by the square root of 36, 6 is 2. So it would look something like this. 2 standard deviations away would be 46. 2 standard deviations above would be 54. That's pretty much what it would look like, right? So now, I could say that if I took 2 down, this is 2 standard deviations, right? 46 and 54, right? 2 times 2, right? So if I were to say, if this were truly the case, right? If I said, I'm going to take a sample of 36 people from this population, right? And it was really a mean of 50 and a standard deviation of 12, 95% of the time, I would expect to get a sample result for my mean, for my sample, between 46 and 54, 2 standard deviations above to 2 standard deviations below. Want to know something? Let's twist this the other way around. In other words, we would expect to be within 2 standard deviations of the mean when I take that sample, 95% of the time. I'm going to turn that around now. And I'm going to say, well, instead of looking at it that way, I'm going to say to myself, let's say that the mean really is 50 for a moment, right? Well, that means that if I took sample and it was 50, I would expect it to behave this way, right? But I don't know that the mean is really 50. So I'm going to look at it this way. I'm going to say to myself, let's assume that my result for the mean is 50, but my level of uncertainty, my range of uncertainty is 2 standard deviations, below and above. Which standard deviation? Not the population standard deviation, but the standard deviation based on the sample size. So I would believe that if my mean is 50, right, which it may or may not be, that if it really was 50, I would add and subtract 2 standard deviations from this, 2 standard errors from this, and I would get a range in which I would expect to get those samples. Well, instead, I don't know it's 50, but since I said if it's 50, I would expect my sample to be within 2 standard deviations. Well, why don't I accept my result of 50 and say, well, instead of my sample being within 2 standard deviations, my true mean is within 2 standard deviations. So in other words, instead of using this to predict what I would get as sample, what I would get as a sample result, I'm using this to predict how well I know the mean. So if I take my result here, X bar is equal to 50, sigma is known, sigma of the population is known, and it's equal to 12, and my sample size is equal to 36. Well, I can say to myself, I'm going to start with my X bar, and I'm going to add and subtract 2 standard deviations, 2 standard errors, right, which I'll calculate now. Standard error is equal to 12 divided by the square root of 36, so it's equal to 2, right? I'm going to add and subtract 2 standard errors, right? So 50 plus or minus 2 times 2 is 4, right? So plus or minus, that's going to be 46 to 54, right? And what I'm saying now is that based on this idea of how this sample distribution works and how I can predict how I can predict if I know where the mean is, what the sample result would be, turning that around, I can also use the sample result to predict how close I am to the mean. So I'm 95%, just like I was 95% sure that I would get a sample between these two numbers, 46 and 54. Now I can say I'm 95% sure, given I've gotten that sample mean, that I'm within 2 standard deviations, or 95% of the true mean. So we're never going to know what mu is. Mu is always going to be unknown to us. But however, now we can take a sample, get a sample result X bar, and we can now, even if we don't know exactly how close we are to the mean, we can say that there's a range within we're 95% certain that we know what the true population mean is, right? So now, where we had nothing before, where we could just take a sample and say, oh, X bar turned out, we think we're near the mean, now we have at least a way to understand how likely it is that we're close to the mean, right? So that's going to come up over and over again, okay? So I'm going to do another one of these. Okay.
Basically, the ones on the side, they're the outliers, or
what's that? Oh no, they're not outliers. It's just that they don't occur as often.
Okay.
In other words,
like
yeah, it's just part of the distribution, but it doesn't occur. In fact, it's interesting you brought that up, because I arbitrarily said 2 standard deviations to the left and the right, right? I could have said 3 standard deviations to the left and the right, right? Except now I'm a bigger z-score, so now I would have had X bar plus or minus 3 times the standard error, right? And that's the range I would have to be 99.7% certain, right? So yeah, those are just occasionally, every once in a while, no matter how far out you go, every once in a while you're going to get a value. So for instance, the population mean is secretly 50. Every once in a while, I'm going to take a sample of 36 people, and I'm going to get 32, right? How often is that going to occur? Super rarely, right? Because it's so far from the mean. The likelihood of getting that extreme of value gets less and less likely, right? That's why the distribution never goes to 0. This is asymptotic, right? So it never really hits that line 0. But, for all intents and purposes, it's 0. In physics, right? they don't consider a result reliable when they have to depend when they're measuring particles and stuff like that. And a lot of that they have to do statistically because they have to see how many released at a given time, and sometimes it's random. You get more now than so. But when they look at it statistically in statistics, they don't consider a result acceptable until they get enough data to be able to say that there's no chance of it being different than what they're looking for by 6 standard deviations. Yeah, we're per public health, we're 2 standard deviations. We're happy as can be, right? That's 95% certainty. That's why people say, oh, saccharin gives you cancer, and then some other study says it doesn't. This study says this, and they redo the study, and you get a different result. And now aspirin is bad for you, and now this is good for you, and so on and so forth. And that's why very frequently you'll see something published. And the first thing will happen when something's published or publish their data, some other school, some other institution is going to try to replicate that result, right? So, I mean, you could argue that at level of 95% certainty, 1 out of 20 studies is not really valid, right? But that you fix that by trying to replicate the results, by doing it again. I got to interrupt for a second. There was because I got to go off topic, right?
Oh, okay.
There was when I was in college, it was like during the Civil War. There was a group that was studying learning in the biological process of learning in animals and various life forms and stuff like that. These guys happen to be working with something called planaria. You know what planaria are? Planaria are tiny little worms, right? These guys did a study where they'll react to light, right? They'll react to food, light, and so on. There's certain stimulus that they'll react to. They trained planaria to turn in the direction of light in response to food, like so on, or turn away from the light or whatever. But they trained them, so they could actually show that the planaria learned, that if they saw this light, they should turn in certain directions, more likely to get food. One of these geniuses decided, let's do an experiment. We're going to take our planaria that we've trained, grind them up, and feed them to planaria that are untrained and see how they perform. They did a study. They did this whole thing, 95% did the whole 9 yards and stuff like that. And they found, according to their study, they were 95% certain that when they fed the naive planaria, the smart planaria, the naive planaria learned faster than if they hadn't been fed the other one. So they must have ingested something. Nobody in the world was ever able to replicate this study. But these guys were still pushing this for years.
It wasn't that they were smart, they were trained.
Yeah, you're not smart, but trained. Yeah. They had there was something in their proteins or DNA or whatever that had, or not DNA, but proteins or brain matter or whatever it is that had benefited these other planaria. Nobody was ever able to replicate this. These guys wouldn't take no for an answer. They still were pushing this for a long time, and it got them into whole other weird areas of study, like ESP and extrasensory and so on and so forth. And the Russians were big on this for a long time. This was very big stuff in the 60s. What do they call it when you're watching something? Oh, subliminal learning. Like you're watching something and then like they flash a message, in a frame that's so fast that you don't actually see it. But the argument is that even though it's too fast for you to actually see it, that the message still got to your brain somehow or other and affected you. And we had all sorts of stuff. They actually published a journal called the Worm Runners Journal, where they published all of these off the wall kind of studies and stuff like that. But that's the danger of this, is that you can think you prove something, but you never really prove anything, right? Because you're always working with a level of certainty. It's great to know that your level of certainty is 95%, but it's never going to be 100, right? And the trade-off is 95% enough, right? If it's really important, maybe you want to be certain of 99%, not 95%. And if it's going to cost a lot of money, it's going to be dangerous. Drug testing, they do multiple studies on drugs, not just one. Right? If they have a conscience, they do anyway, right? So they do multiple studies on drugs. But still, things get through turn out in the future studies that are larger, bigger, better
How
to
about
be.
medication? Is it at 3 deviations or 2 deviations?
Right.
Like pharmaceuticals, that there's a new drug.
I had a friend of mine that worked for Bristol Myers, and I had two friends that worked there, completely unrelated. Just happened to know them completely separate. One I knew from some computer club back in the 60s, 70s, and the other one was a good friend of mine from college who worked as a brand manager at Bristol Myers. And this other guy was a dentist, right? And the dentist and a physician. And he wound up working for Bristol Myers testing products and stuff like that, right? And my friend Charlie, one time, we got together for dinner or something like that, years after college, decades after college. And I said to him, oh, by the way, I was talking to this guy and he worked at Bristol Myers, in your testing division and stuff like that. Do you happen to know him? I said, his name's Wally Elverst, right? He's passed away. I'm sure by now. He says, oh, yeah, I know Wally. He says, oh, wow, no kidding. Yeah, Wally's the guy that whenever we had two good tests, always wanted to do a third. So yeah, that's, that they have to make decisions about this. They don't want to be too careful, because if you get a study, even if the drug's good, you can get the other kind of result where it's a good drug, but you didn't have enough sample size or you had an odd result, and where the drug worked, you may not have proved it with that study, right? So then you got a kind of an argument about how close did you come and so on and so forth. So it cuts both ways. Okay, so getting back to the point here, right? So now, if I do a study now, and I want to say to myself, well, okay, I take a sample of size 100. My sample size is going to say it's blood pressures, diastolic blood pressures. My mean blood pressure for these 100 people is 80, and my standard deviation for blood pressure is equal to 10, right? Well, my standard error is going to be equal to 10 divided square root of 100, which is 10, is equal to 1. My standard error is equal to 1. So now I want to say to myself, well, I found that it's 80 in my study, but nobody's interested in what the mean was in my study. They want to know what is the mean in that population. So I'm going to present this with a confidence interval. I'm going to say X bar, right, plus or minus. I'm going to say 2 standard deviations. I'm going to write that very lightly for the moment. I'm going to call it standard errors because it's really standard errors times, 2 standard errors, 2 times standard errors. Okay, I'm going to write that all relatively lightly. Now, remember that 95% in our normal distribution from the empirical rule? Was it really exactly 2 standard deviations? That was an estimate, right? If you look up the Z table, it's really, I don't have it handy. It's 1.96 standard deviations is 95%. So instead of adding and subtracting 2 times the standard error, I'm going to say 1.96 times the standard error, which turned out to be 1. So my 95% confidence interval is going to be 80 plus or minus one times 1.96 plus or minus 1.96, not 2. Right? This part over here, which is 1.96 times standard error, this I'm going to give a new name to. It's called my margin of error. Right? That's a good name, right? Because plus or minus kind of sounds like margin of error. So 80 plus or minus 1.96 is going to be 78.04 to 81.96. So I may not know exactly what the mean is of the population, but I can say with 95% certainty that it's between 78.04 and 81.96. And you'll see when you read the abstract to a study, most people just read the abstract, right? I mean, unless you're really involved, you don't get past the abstract. You just want to see what they did, what the results were, and stuff like that. If you're a researcher in the same area, then you read the paper, right? And you see all the statistics and all the important stuff. But in the abstract, in the summary of this whole thing, they always, if they give you a result for a numerical variable, like blood pressure is 80, they'll put right next to it, they'll put the confidence interval. They'll say 95% confidence interval, 78.04 to 81.96. So that when you say that kids in the Bronx have a blood lead level of 4.2 micrograms per deciliter with a confidence interval of 3.0 to 6.2, right? That's their average blood lead level. When you see that, you say to yourself, oh, that's what the average was. But then that means they're 95% sure that the real average is between those two numbers. Why is that important? Because that result, the action level, EPA action level for blood lead level in children is 5 micrograms per deciliter, right? Okay, so if you look at that average, you say, oh, on average, these kids are below the action level, right? But if you look at the real result, oh no, they may on average be above. You don't know that it's really different than the action level, lower or higher than the action level. So it's important to know how well you know that mean, right? And since we'll never know what the true mean is, right? This is the closest we can get, is this idea of a confidence interval. Okay? Make sense? Right? Pretty cool, right? Okay. So so now I'm just going to complicate it just a little bit more because you brought something up that I wasn't intending to cover, but it's good you brought it up. And that is that I said X bar plus or minus 1.96, and I didn't choose that 1.96 at random, right? I chose that because that represents 2 standard deviations to the left and the right. Well, let's say that's the 95% confidence interval. What? So I'm sorry. Yeah, well, standard. I'm using standard error because we're always using this formula with a sample, right? Let's say that I want it to be 99% certain. Well, that's going to be X bar plus or minus something times the standard error, right? What's it going to be? Let's think about this for a second. If you want to be more confident that you have captured the mean within that range, do you want that range to be wider or narrower? If you make it wide, like for instance, if I told you to guess at my age, right, and you wanted to be more certain that you got my age, right, you wouldn't say, 82 to 96, right? You'd say 75 to 115, right? The wider it is, the more confident you are. So we want this interval to be wider, right? So this number is going to be bigger than 1.96, right? What's it going to be then? Well, since we want to be 99% certain, we picked 95% certain because it's 2 standard deviations above, 2 standard deviations below. 99% certain, we need 0.5% in that end and 0.5% in this end. If you go to the Z table, the Z number that represents 0.5% on this end, 0.5% on this end is 2.58 standard deviation, 2.58. Z score of 2.58. That's, if you want to be 99% certain, that's what you would use instead. Well, how about if you only need to be 90% certain? Okay, I'm not going to torture you with it, but you can imagine if you're willing to be on 90% certain, it can be narrower. So the margin of error can be smaller. So X bar plus or minus 1.64 times the standard error. If you write down or remember those 3 numbers, right, you probably are never going to have to go to a table to look up the correct number, because those are the ones everybody uses most of the time. Okay, so that's how we deal with this whole thing. Okay, so now, this doesn't just apply to, we didn't really get, I don't know how much of this I really got to in the online videos. As hard as this is to believe, I don't watch every minute of the online videos when I put them up sometimes, because if it's an old video, I made it like last year, I'll say, oh yeah, I remember, I'll scrub through it, and but I may not remember everything I put into it, whether it's in this week's or next week's. It might be in this part might be in next week's. Okay, so now let's say you have a proportion, right? Let's say that we have a situation where we do we're doing a political poll, for instance, and we sample 1,000 people, and out of those 1,000 people, 550 of those people say that to this proposition that's on the ballot, they're going to vote yes. Right? The other 450 say they're going to vote no. So what proportion is voting yes and voting no? Well, 550 out of 1,000 people, the probability of an individual voting yes is 0.55, right? 550 out of 1,000 people are going to vote yes. Okay, so now you're saying to yourself, oh, this proposition is going to pass, right? Where, because it's more than 50%, it's gonna pass, right? Well, wait a second. We're not sampling everybody. That's what an election does. It samples everybody, right? We're only sampling 1,000 people. Could be 1,000,000 people. If it's New York State, could be not maybe not 1,000,000, maybe 700,000, 800,000 people actually voting on this proposition in New York State, right? So we don't really know what the true p-value is. We only know what the sample p-value is. Now, remember when we did x bar instead of in order to signify the mean of a sample? When we do that with the proportion of the population, we use p, and we use p with a cap on it for the proportion of the samples. That's p cap. I need to know the same thing. How well do I really know that? Well, I'm not going to know it until they have the election. This is not going to be known to me until the election actually takes place, where we actually count everybody, right? But in the meantime, I have this based on 1,000 people, which is a really big sample, right? We have this, but how well do I really know what P is? We do exactly the same thing. We say P cap plus or minus 1.96, if I want to be 95% certain, times the standard error. Okay, so P cap is 0.55. That's pretty simple. Just saying, it's just an analogy with the other thing that we did. So what about standard error? Well, in this case, the way we calculate standard error, I won't go into the derivation of this, but standard error is equal to the square root of n times p times 1 minus p. Do I got that right? No, that's binomial binomial distribution sample. Okay, standard error is equal to the square root of p times 1 minus p over n. I'm having a senior moment here. Okay, let's see if that works out. That's equal to 0.5 square root of 0.55. 1 minus p is 0.45. 0.45 time over 1,000. Let's see what that works out to be. This part over here was something else. This is finding the standard deviation of when you take the binomial distribution, which we may have covered a couple of weeks ago. I didn't bring it up in the test, right? That was you may have covered because you don't use it too often. Huh?
Yeah.
It was on the test? Okay. That's from the normal approximation to the binomial distribution, right? Similar, same idea. It's a proportion, right? The binomial distribution is really a proportion, yes and no, right? So at any rate, so this is okay, so this is, let's calculate this. It's in my head. It got stuck in my head. That's why I wrote it there. Okay. Okay, so this is 0.55 times 0.45. That's what we have here, right? And we're going to divide that by 1,000, the sample size. And that's equal to that. And now I'm going to take the square root of that. And there's the square root of that. Whoops, no, I did that wrong. I squared it. I hit the wrong thing. Hang on a second, let me do that again. 0.55 times 0.45, right? Divided by 1,000 is this, and we're going to take the square root of it, this down here. And it comes out to be 0.016. I'm going to round it off to 0.016, 1.6%. So if I go back here, it's 1.96 times 0.016, right? So I'm gonna make believe this is 2 for our purposes right now. 0.55 plus or minus 2 times this, which is equal to 0.032. Okay, so 0.032, okay, if I add and subtract it to 0.55, that's going to be 0.518 to 0.582, I think, right? So I'm 95% certain that the true population proportion is between 52% and 58%. right? So now what does that mean? Since I only need 50% of the vote to win, that says I'm 95% sure I'm going to win. Had this come out to be 0.490 to 0.570, I would not have been 95% certain that I really had 50% of the vote. I would have needed a bigger sample size so I could get a narrower range.